So I'm not going to give you an implicit function. I'm actually going to give you an explicit function. X raised to the power x. That's an explicit function, right? This is not an implicit function. I want you to find the derivative of this. Okay. So let's start talking about this. What type of rule do you think we might use to differentiate this function? So you're just finding the derivative, that's it. You say just finding it, Hirsch, as if it's so easy.
I mean, is there like a trick to this, or?
Is there a trick? Jacqueline thinks I'm always tricking everyone. So I don't know. I guess I am. So Caleb, you said power rule. Okay. So what would happen if I were to use power rule on this, Caleb?
It'd be like, let me see. X, I don't know.
X?
Like
Okay,
X
so now you
times
don't know?
X.
X times X?
Yeah, it's like a bunch of weird.
It's a bunch of weird
To
X's.
the X minus 1.
Okay, good. So X times X to the X raised to the power 1, and then I can actually recombine them. I can get, this is X to the 1 times X to the X minus 1. They actually recombine and give you back X to the X. Isn't that nice? That's very convenient. Now I see a lot of chain rules. Miriam, you're saying chain rule. What do you think is the outside and inside function if you're going to use chain rule?
Wouldn't the inside function be the to the power of x, and then the outside function be the normal x?
Not quite, because if my outside function were x and my inside function were x, this is the function, this is the identity function. It's the function that just returns the same value. And then inside that, I do the function that returns the same value. So actually, if you compose these two functions, if you do f of g of x, you just get back x. You don't get x to the x. So not quite. Are there any other ideas of what to do here? Logs, Justin? Okay, no, you took calculus. No, you don't get to answer. You're a ringer. So, Jacqueline, you said it's the same thing, right? Huh? What's the same thing? What did you mean by this comment?
You can't use the chain rule, I think.
Yeah, so we just discussed how you really can't use the chain rule. Can I use this power rule? Is this correct what I've written down?
I mean, it's
Why?
correct. It gives you
You
the
think it's
same.
correct?
It
It's
gives
not.
you the same thing, so it's not like finding anything new.
So this is not correct. Why is this
Yeah.
not correct?
Um,
You don't necessarily have to answer. Someone else can, if you want to. Why is power rule not okay here? Not a constant. Specifically, what is not a constant?
Because x is like another function, maybe it's not. I don't know.
Okay, of these two x's, which one should have been a constant for you to be able to use power rule? The exponents, Simran answered. Right, so the exponent is not a constant, so you can't use power rule. Now, I see a lot of LNs. I see a lot of LN businesses going on. Okay. I also want to mention you also can't use this exponential rule. Why? Because the base is not an exponent. Oh, sorry, the base is not a constant. So if I have both the base and the exponent are both not constant. Ayana's just giving us the whole answer. Is it obvious how Ayana got that answer? X to the x times ln x plus 1? Could you do change of base rule, then solve for the derivatives of that? Okay, so let's discuss how you actually do it. Okay, so the main thing I want you to realize first is that none of the rules that we have directly apply to this function. So we need to be clever. Now, that's why, so especially for those who have not taken calculus and you don't know the answer quite just yet, if you're looking in chat, we see a bunch of people saying something about logs, something about exponents, right? The idea is that our rules are not, I mean, they are sufficient, but we do have to rewrite this function. Remember a long time ago I said how you write a function very crucially affects what rules you use. So we have to rewrite this function in such a way that we can actually use our rules. So there's going to be two methods that I'm going to show you. So let's look at method number 1. I think someone did mention method number 1. Let's look back at the chat. Let's see who is the lucky person. Mohammed, what did you mean by e to something? What did you mean by that?
I was saying if you put the whole thing e to the natural log of x times x, then you can maybe solve it.
Okay, good. So actually that's the first method we're going to talk about. We can rewrite the function just using regular log rules. So my function is x to the x. Remember that e and ln cancel each other out. So does it make sense for me to say that this is equal to e to the ln of x to the x? Yes, right? Because the e and the ln's just cancel out and give me back the original. I mean, it's kind of like a stupid thing to do, introduce this e to the ln. But everyone should agree that these two things actually are equal to each other. But now, why is this actually convenient? Because this x is an exponent, so it can come outside the ln as a coefficient. And so now I have the e to the x ln x. Now, by rewriting the function like that, what have I actually done? I have rewritten this in such a way that now I actually can use chain rule. Why? What is the outside function? What is the inside function? Who wants to tell us that? After I've rewritten the function like this using basic logarithm rules, I can now think of this as a composition of two functions. What's the outside function in this case? Outside is e to the x. Very good. What is the inside function? X ln of x. Not just ln of x, it's x ln of x, right? It's the whole exponent. Okay, so now when I use chain rule, so I'm going to call this method 1. I'll call it just rewrite function. Okay, so now when I do chain rule, f prime of x equals, so I get the derivative of the outside function. So I've said this a few times. If you have an e to the something, the derivative is just the same exact thing, right? Because e to the x has its own derivative. But now by chain rule, I need to multiply by the derivative of the inside function, the derivative of the exponent. And for that, I need product rule, right? 1 times ln x plus x times 1 over x. And if you want to simplify, e to the x ln of x, we already know as x to the x. That's the original function. And here, the x and 1 over x cancel each other out. So you can write this as x to the x times ln x plus 1. Nice. Actually, I'll just write it over here to save a line. Now in the notes, we won't have that extra line, so get rid of it. Okay, now there's a second method. And this is actually, this is a whole subsection in your textbook. This is called logarithmic differentiation. Now, neither of these methods is required. Like in the sense that you don't have to pick one over the other. They both work. I will say that logarithmic differentiation is oftentimes the easier option, only because the expressions you're dealing with are very large, and it's kind of annoying to write everything in the exponent. But yeah, both methods are perfectly fine. So how does this actually work? So this will also show you, well, why was this in the implicit differentiation section to begin with? So this is where we're going to use implicit differentiation. So we start off with, we have y equals x to the x, right? That's our function. Okay, so that's my original. Now, a lot of people said this in chat, take the logarithm of both sides. Okay, so I take the log of both sides. Okay. Now what do? Well, the whole point of logarithms, now we are going to see this again when we do L'Hopital's rule. The main advantage of logarithms is it turns exponents into products, right? X to the x is an exponent, right? It's an exponential. But now I know that this comes outside as a coefficient, right? So logarithms turns exponents into products. That is the main advantage of logarithms. So I'll just call that log rules. And now I differentiate, right? Now I use implicit differentiation. So actually, it's easier if I put explanation on the left-hand side. So on the next line, we're going to use implicit differentiation. Okay. So implicit differentiation. If I differentiate the left-hand side of this equation, what do I get? What is the derivative of ln of y?
One over y.
Well, Justin has a typo. I think Justin knows it. Oh, there we go. It's not just 1 over y, right? Why is 1 over y not the full answer? What is forgotten if you just write 1 over y? What did you forget to do? You need to take the derivative of the denominator. The derivative. So what rule did we miss? What rule did we forget to apply to this? Chain rule. That's right. Exactly. Y is the inside function here. So the derivative of the outside function is ln. The derivative is 1 over whatever is there. But then y is inside, so I need to multiply by the derivative of the inside function according to chain rule, which is dy dx. Okay. And the right side we just have a normal derivative, just product rule, right? So that's no mystery. And now we can solve for dy dx. So on the right side, I simplify, I get ln of x plus 1, and then I multiply the whole thing by y to cancel that on the left-hand side. And then I replace with original. So the original function was given to me as an explicit function of x. So the derivative should also be an explicit function of x. Your final answer should not include a y in it. It should be with x's. So y was equal to x to the x. So just make sure to replace that. That's all. And now I can actually write down, I can call this f prime of x instead of using the dy dx notation. Okay, any questions about that method? So that is called logarithmic differentiation. Notice how basically it's called that obviously because you take the ln of both sides, used to start with essentially, and then you use implicit differentiation. Questions about any part of that?
What happened to the 1 over y?
Well, we canceled it out. Remember, we're solving for dy dx. So how do I solve for dy dx? I multiply both sides by y.
Okay.
Right? So to cancel that out on the left-hand side.
Okay.
So that's algebra, right? So at this point, this is the last line you do calculus. Everything else is algebra.